In this short video, we are going to talk about motion in space. We're going to actually do this in two parts. So, motion in space, we've already examined in Calc 1 and maybe other courses how to study motion in a straight line, maybe even motion in 2 dimensions. But we could look at the vector representation of a curve. If I consider the t parameter to represent time, then it would be the position function of, say, a particle at any given time t. And in that case, we can define velocity in the usual way as the rate of change in position divided over time. And so that's the same thing as r prime of t. See, I have a typo there. I guess it's not a typo, a handwritten error. Now, the speed of the particle is going to be denoted with a lowercase v with no arrow. So we have to really pay attention to, do we have an arrow or not an arrow? No arrow, speed. Arrow, velocity. So it'll be the magnitude of the velocity. And again, with an arrow, v with an arrow, it represents velocity, and v without an arrow represents speed. And then if I take the derivative of velocity, just as I did in previous classes, I'll get the acceleration. And it'll be the second derivative of the position function. So let's see if we can use that idea to solve this problem. We're given the acceleration function. We're given the velocity when time equals 0, and we're given the position at time equals 0. So we call this the initial velocity and the initial position. So we'd like to find all three functions, the velocity function, the speed function, and the position function, working backwards from the acceleration function. Well, velocity will just be the antiderivative of acceleration, even when it's a vector function. So let's take the antiderivative of the given acceleration function. We'll do that one component at a time. We'll get this antiderivative plus a constant vector of integration. So we need to evaluate what this c1 vector is. Well, we can use the fact that the velocity at 0 has components 1, -1, and 1. So let's go ahead and put 0 in the place of t in my expression for the velocity, and that just gives me all zeros. And so that will lead me to say that C1 is just 1, -1, 1. So I put a little caution sign here to warn us that this is not always the case. I see a lot of time people just assume that, oh, the initial velocity is going to be this C1 vector. That's only the case here because when I replace t with 0 in my antiderivative, I got all zeros. But I could have easily had an e to the t or a cosine of t, and e to the 0 is 1, cosine of 0 is 1. So I have to be careful and actually make sure I solve for C1 and C2, as we're going to see. All right, so now I've got my velocity function. I have 2t squared plus 1. That's for my constant. 3t squared minus 1, and then -2 sine t plus 1. So the position, before we do the position, don't want to forget the speed. So speed is just the magnitude or the length of that velocity vector. So I'll take the square root of the sum of the squares with these first, well, all of the terms actually. I need to use FOIL. So I'll get 3 terms from the square of the first component, 3 terms from the square of the second component, and then 3 more terms from the square of the third component. And there's a few like terms, so I can clean that up a little bit. All right. Now let's go to the position function, which will just be the antiderivative of the velocity function. So I have my velocity function here. Let's just take its antiderivative, one component at a time. And then I will also get a second vector of integration. So let's use the initial position to help find the components of this C2 vector. So now when I put 0 in the place of t in my antiderivative here, I will get 0 in the first and the second components, but since cosine of 0 equals 1, the third component is 2. So I'm going to actually have to solve for C2. So I'll have, well, 1 minus 0, then 0 minus 0, but then the third component will be 1 minus 2. So my C2 vector is 1, 0, minus 1. And so now that I have the C2 vector, I can write out the entire position function. So here's my velocity function, my speed function, and here is the position function. I just needed to add the components plus 1, well, 0, and minus 1 to my antiderivative. Let's talk about projectile motion in the plane. So we are going to be looking at some projectile that's moving in the xy plane. And so what we do is we have a projectile like a baseball. It's launched with an initial speed v naught, v sub 0, at an angle of theta with the horizon. So this is highly simplified. We're going to ignore wind resistance and other factors. The only force affecting the projectile in flight is the force of gravity. So the acceleration vector here, it has only two components. So the horizontal component is 0. There's no acceleration in the horizontal direction. And in the vertical direction, the only acceleration is due to the acceleration due to gravity. And that's what the G stands for, the acceleration due to gravity. So our goal here is, in this example, is to find a formula for the position function of the projectile in flight. So what we're going to do is we're going to draw a triangle here. We're given some initial speed, which is the length of the velocity vector. We know that the angle made with the horizon is theta. So for some triangle trigonometry, we can say that this velocity vector has two components. The horizontal component is the initial speed times cosine of theta, and the vertical component is the initial speed times sine of theta. So our velocity at time 0, or v naught, is initial speed times cosine theta, comma, initial speed times sine theta. And then for the initial position, we're just going to call its components x naught and y naught. That is the position at time equals 0. So we're given this acceleration function, and we want to get to the position function, making use of these initial conditions. So to get to the velocity first, we'll take the antiderivative of acceleration. We are going to get a vector constant there. And so if I use the initial condition for the velocity, that will tell me that that c1 vector is going to be v at 0, so the initial speed times cosine theta, comma, the initial speed times sine theta. So that will be our velocity. If we ever needed a formula for velocity, it would have those two components. But we'd like to find the position, so we'll take the antiderivative of the velocity vector. And of course, after I take the antiderivative of each term, I will get another constant of integration, but we'll just use the initial conditions for the position. The initial position has components x naught, y naught, so those will be the components of C2. And so our position vector is going to have two components. We'll have the initial speed times cosine theta times time plus the initial position in the horizontal direction. And then the vertical component is going to have three terms. It's going to have the initial vertical displacement, and then the initial speed times sine theta times t, and then subtract off 1/2 gt squared. So let's use that formula in another example. So let's stick with baseball. A batter hits the ball with an initial speed of 122 feet per second. That's about 83 miles an hour. From a height of 3 feet above the ground and at an angle of 30 degrees with the horizon. And so it's headed straight to the left center field where there's a fence, which is 8 feet high. And the question we'd like to know is, does the ball go over the fence, which is 385 feet away? And we're told to use 32 feet per second squared for the acceleration of gravity. So here's our formula. What's our strategy? Well, we'd like to say, let's find the value of t when the horizontal component is 385 feet. And once we know that value of t, so we've got all the information to solve for t. We know the initial speed. We know that the initial position is 0. We know theta is 30 degrees, so we can find cosine of theta being root 3 over 2. We can solve for t. Then we use that value of t and substitute it into the vertical component and see what the height is. If the height is greater than 8 feet, then we can say, yes, the ball does make it over the fence. If it's less than 8 feet, then the answer would be no. So let's review. Our initial speed is 122 feet per second. We've got an angle of 30 degrees. Our initial position in the horizontal direction is 0. In the vertical direction, it's 3 feet off the ground. And we're told to use g equals 32 feet per second squared. So our horizontal component would be then 122t times cosine of 30 degrees, which we can evaluate. It's root 3 over 2. And we want to set that equal to 385 and solve for t. So yeah, evaluating cosine of 30 degrees, solving for t and getting a decimal approximation. T is about 3.644 seconds. All right, so now that is when the horizontal distance now is 385 feet. The question is, where is it relative to the ground? Is it above the ground, below the ground? Is it above the fence, which means its height would have to be at least 8 feet. So we go ahead and substitute our given values in. We put in 32 for g, take half of that. 122 is our initial speed. We've got sine of 30 degrees, and we started from a height of 3 feet off the ground. And if I substitute 3.644 in place of t, I get about 12.8 feet, which is certainly more than 8 feet. So the answer is yes, the ball does clear the fence. Got a home run. All right, we're going to continue our discussion of motion in space in our next video.